So let's say we have a 7 by 7 grid that holds a certain number, and we want to understand how a neural network of an AI can be able to recognize that this is the number 1. For us as human beings, we can easily say that this is the number 1. And in this video, I will be teaching you in simple terms how an AI system exactly can know that this is the number 1. So, for that, we will split this matrix of 7 by 7 pixels, which is 49, into different numbers varying between 0 and 1, describing the intensity of that pixel. So, if a pixel is lit up, like here, it will have the number 1, and if it's turned off, it will have the number 0. So we have exactly 49 pixels in that grid. So for that, we will have 49 neurons in the input layer. 1, 2, 3, etc. to 49. Okay, so we have 49 input neurons. Each neuron holds a number between 0 and 1, which is called the activation. So for that pixel, which is described in this neuron, it will be holding the number 0 because it's turned off. And for the second one also, for the third one also, but for the fourth one, which is here, 1, 2, 3, and the fourth one will be 1. In reality, the number is between 0 and 1, which represent how black or how white the pixel is. But here, for simplicity, we will say that it's either turned on or off. Okay? So this is for the input layer. And of course, for the output layer, we will have 4 options, which is either the number 1, number 2, number 3, number 0, number 1, number 2, or number 3. So we will represent them as 4 neurons on the output layer. It's in red. So, after the process is done, one of those neurons will be of a higher probability. They will all have a number between 0 and 1, and the highest number represents the number. So, this neuron represents the number 0, the number 1 here, the third neuron represents the number 2, and the fourth neuron will represent the number 3. Okay? So, let's say the process is done, and at the end, this neuron is lit up, this. So we know that the prediction of the AI is the number 1. Okay. The mathematics and the genius is between the input layer and the output layer. And here we have the middle layer, which consists of also many neurons. So there is a connection between each neuron of the input layer and each neuron of the middle layer, represented by this, like this number 1 neuron in the input layer is connected to all these neurons of the middle layer. And the same thing for the second neuron. And the same thing for the third, etc. to the 49th. Okay? So, for simplicity, we will only be studying right now how does one input neuron is connected to one middle neuron of the middle layer. Okay, so let's say we have a grid line here. Sorry, we will study how all the input neurons are connected to a single neuron of the middle layer. Okay, so those lines in green are called the weights, and they are noted W. And here exactly we have 49 layers between all of the input layer neurons and the first neuron of the middle layer. Okay, so how exactly are they connected? Let's bring it to here and say that this is the first neuron of the middle layer, and those in blue, we will take a sample of 3. Okay, F3 to facilitate things and make it more simple. But exactly we have 49 connections. Each connection will hold a weight, and we will see what is the weight. So we will study 3. This is weight 0, weight 1, and weight 2. This is activation 1 of the input layer, activation 2, activation 3. So, sorry, neuron 1, neuron 2, neuron 3, and each of these neurons holds what is called an activation given by this input grid. So, the way they are connected mathematically is, we can easily say that, or easily write that the mathematical function is like this: A1 times its weight, so, sorry, those are the 0, 1, 2, A0 times W0 plus A1 times omega 1 or W1 plus A2 times W2. So this function or this mathematical summation will give out or spit out a certain number which can vary, which can be a negative number, a positive number, it doesn't matter, because weights are numbers that may vary. They may be -4, +6, 0, etc. So in order to spit out a number that we will put here, we will be putting here a number between 0 and 1. So we will need what we call an activation function that can squish that big number or negative number or 0 or whatever number into a single number between 0 and 1 that can represent the activation of that neuron, which is here inside our system, our neural network. So an example of that function is called the sigmoid function, which is like this. We have the x and y axes, and here we have the sigmoid function, which is like this, that takes any number between like -infinity to +infinity and gives out a y, the y, between 0 and 1. Okay, so this is the function. And what is this function? It's called the sigmoid. It has this symbol, and it's 1 over 1 plus e to the power of -x. So we put that summation inside the sigmoid, and we have something like this. That's a square root, sorry. Something like this. So to make this neuron, or the connection between this neuron and all the neuron of the input layer, or any two combination of, like between this neuron and this neuron, or this neuron and this neuron, or between all the middle layers. We can have multiple middle layers. Here we have one for the sake of simplicity. We will be adding something called a bias inside the parentheses. So we will have something called a bias, and I will note it in black. We will subtract the bias from all of this. So if you want to make it, if you want it to be like more sensitive, we will lower that bias. If you want it to be like less sensitive, so it will need a very high value to be able to be a number that is very close to 1, we will a higher b. So the higher the bias, the less sensitive is the function. Okay? And at the end, as a mathematical form, we will say that we have the sigmoid, and we will represent this as a matrix, as a combination of matrix. Two of them are a product of two matrices, and we will add the bias. So we will have here the matrix that holds W0, W1, W3, etc. And the same thing for each and every neuron. So here we have 0, 1, 0, 0, 1, 0, 2, 0, 3, 0, 4, 0, 2, 49, 0. So we have here 0, 0, 1, 0, 2, 0. And here we have 1, 0, 1, 1, 2, 1, and etc. And here we will make the dot product with A, which are the activations. We will have here A0, A1, A2, and if we have more, we can continue. Then we will add the bias, B0, B1, B2, etc. And we will wrap it all inside the sigmoid function. And this representation in simple forms is W times A plus B, and all wrapped in a sigmoid function. So this is how easy it is. And in the next video, we will see how those biases, weights, and activations are tweaked to form the neural network that is smart enough to recognize this number 1.